हेलो फ्रेंड्स, वेलकम टू ट्रूथ ऑफ फिजिक्स। आज के इस वीडियो में मैं डिस्कस करूंगा बोसोनिक कम्यूटेशन रिलेशंस के बारे में। ठीक है, तो सेकेंड क्वांटाइजेशन नोटेशन को हम यूज करके बोसोनिक कम्यूटेशन रिलेशन को प्रूव करेंगे। सो व्हाट इज सेकेंड क्वांटाइजेशन? फर्स्ट लेट अस अंडरस्टैंड ब्रीफली। ओके, सेकेंड क्वांटाइजेशन, फॉर एग्जांपल सपोज वी हैव अ सिस्टम। ठीक है, हमारे पास कोई भी एक सिस्टम ऑफ पार्टिकल्स है। ठीक है, और यहाँ पे हम हमारे पास कुछ एक्साइटेड स्टेट्स है। ठीक है, ये सपोज हमारा फर्स्ट एक्साइटेड स्टेट है, सेकंड है, थर्ड है, ऐसे एक्साइटेड स्टेट्स है। तो सपोज हमारे पास दो पार्टिकल है इस सेकंड एक्साइटेड स्टेट में। तो फिर हम इसे किस तरह से डिनोट कर सकते हैं? हम एक एक रिप्रेजेंटेशन ऐसा हो सकता है, हम मल्टी पार्टिकल स्टेट को डिनोट कर रहे हो। ओके, मेनी बॉडी सिस्टम के लिए। ठीक है, तो हम एक तो नोटेशन ऐसा हो सकता है कि इसको हम ऐसे लिखते हैं 2,2। मतलब फर्स्ट जो पार्टिकल है दिस, इट इज इन द सेकेंड एक्साइटेड स्टेट, एंड द सेकेंड पार्टिकल this is also in the सेकेंड एक्साइटेड स्टेट। तो ये है एक नोटेशन, लेकिन हम इस नोटेशन को यूज नहीं करेंगे। हम रादर यूज करेंगे सेकेंड क्वांटाइजेशन नोटेशन, दैट इज ऑक्यूपेशन नंबर रिप्रेजेंटेशन। ऑक्यूपेशन ऑक्यूपेशन नंबर रिप्रेजेंटेशन। तो ये क्या है? ये कुछ इस टाइप का है कि हम इसे लिखेंगे 0,2,0,0,0 दिस। सपोज देयर आर मेनी मेनी स्टेट्स। ओके, सो ये क्या हुआ? मतलब द फर्स्ट एक्साइटेड स्टेट, दिस डिनोट्स दैट द फर्स्ट एक्साइटेड स्टेट हैज जीरो नंबर ऑफ पार्टिकल्स। राइट, यहाँ पे कोई भी पार्टिकल नहीं है। एंड द सेकंड एक्साइटेड स्टेट इज डिनोटेड विद दिस is what? There are two particles. So these numbers, that is 0, 2, 0, these numbers are actually denoting the number of particles in that perspective state. Okay, okay, now we'll use these notations. Okay, now for bosonic states or bosonic systems. Okay, suppose let us have a system, or let us have a state like this. What is denoting? What I am denoting with this? This means that we have a bosonic state with n number of particles. The number of particles in this state is n, right? According to this representation, occupation number representation. So there are n number of particles in any state of a system. ठीक है, तो n नंबर ऑफ बोसॉन है उनका, वो एक ही स्टेट में बिलोंग कर रहा है। ठीक है, n नंबर ऑफ बोसॉन एक ही स्टेट में बिलोंग कर रहा है, और वो स्टेट को हम इससे डिनोट कर रहे हैं। नाउ हम क्या करेंगे? और यहाँ पे बोसोन के केस में हमारा जो नॉर्मल हमारा हार्मोनिक ऑसिलेटर का जो हमारा जो क्रिएशन एंड एनिहिलेशन ऑपरेटर्स होता है वही फॉलो करता है। मींस हमारा जो एनिहिलेशन ऑपरेटर है हार्मोनिक ऑसिलेटर को, वो सपोज फॉर दिस इज सपोज आई एम डिनोटिंग विद 0 means this is for ground state. Okay, this is suppose for ground state wave function, where state gate. So annihilation operator acting on this gate gives what? This will annihilate one particle, right? Now, so the number of particles now becomes n minus 1. So the state will be now denoted as n minus 1 gate. This. Okay, and there is a prefactor. We know from the study of harmonic oscillator, we know that the prefactor will look like something like this, and its pair means the creation operator will look something like this. Suppose it is acting on the same gate, then it will create one particle in the state, and the prefactor will be root over n plus 1. ठीक है, तो फिर हम इस चीज को यूज करके कम्यूटेशन रिलेशन को डिराइव कर सकते हैं फॉर बोसोनिक स्टेट्स। तो हम यहाँ से समझ सकते हैं, इसका अगर कॉम्प्लेक्स कॉन्जुगेट लेते हैं हम, ठीक है, तो हमारा कुछ इस टाइप का आएगा a नॉट, राइट, एंड दैट इज इक्वल्स टू, ओके, हम इसका ले रहे हैं। ठीक है, तो a नॉट डैगर हो जाएगा ये, एंड दिस इज इक्वल्स टू आवर n minus 1, and this is just a number, right? So root over n. Now if we denote it with 1 and denote it with 2, then if we do this inner product like n a naught dagger and a naught n, then what we'll get? Then we'll get, this is just a numbers, so this will become n, and this n minus 1 and n minus 1. Now due to the orthogonality relation, that is for states containing different number of particles, the orthogonality condition looks something like this: n m, this is Kronecker delta n m. Okay, so according to this relation, this will become n. So this is becoming n, means n is what? N is the number of particles in that state, right? Number of particles in that state. That means this thing, what is this thing? This thing is behaving as a number operator. Means if we denote it with n not this symbol, then this acting on this will give us what? Will give us n, right? Then if we take the expectation value, then we'll get n back, right? So this is called the number operator, we know, right, from the study of harmonic oscillator. Okay, similar thing. Now we can write another thing like so in this state can be written as a naught is dagger, means the creation operator acting on what? N minus 1, right? But we are missing something, right? If this operates on this, then there is a prefactor which is nothing but root over n minus 1 plus 1, means root over n. So we have to divide it with root over n, or I can write it with a naught its dagger, then another a naught its dagger, then what? N minus 2 with under root over n into root over n minus 1, right? Similarly acting on n minus 3 state, and similarly doing the steps again and again, we can write it like a naught its dagger whole to the power n, because there is n number of particles, whole to the power n, and then what? 0 state, and divided by root over of n factorial, right? So this is a generalization. We'll use this result often. Now dagger, its commutation, what will be that, right? So for finding that, we have to do what? We have to act this on any state get n, suppose. So a naught dagger and n minus a naught dagger, a naught and n, right? So what will get? This when act on this gives a root over n plus 1, right? And then when this act on this total thing, we'll get root over n plus 1, means n plus 1 and n, right? Sorry, so this thing. So we'll get n plus 1 and the kate back, minus if we add this thing, and this you can see that this is the number operator, right? We have discussed before the number operator n naught. So it will just take out the number of particles in that state, this and then this. So what will get? We'll get n plus 1 minus n, and then get back the same kate n, right? So what we'll get? We'll get simply this thing, 1 into this, means a naught dagger, this commutation relation, okay, or this is denoted also with this means the commutation relation, right? Means there is negative sign, okay? So this is another symbolic representation. So for bosonic single state, a naught comma a dagger means it is coming out to be 1, right? Because this is 1, right? You understand, right? This acting on this state gives 1 times this, means this is equals to 1. Okay, now let us generalize this for many states. Means suppose we have a state, it is a representation. Okay, this we have a state like this, n0, n1, n2, dot dot dot. Means what it represents in the operation number representation, means in the 0 means suppose the ground state, okay, of that system. Ground state, first excited state, second excited state, and this way. So this means that there is n0 number of particles in the ground state, n1 number of particles in the first excited state, n2 number of particles in the second excited state, and so on and so forth. So what we'll get, okay, now if we apply the annihilation operator on, annihilation operator now becomes something like this. Means that what is this denoting? This, if it acts on the total this thing, means n0, n1, dot 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 dot. There is them in L, right? Means this means what, the L8 excited state has n L number of particles, right? So what it will act, it will do, or it will just annihilate one particle from that state, from the L8 excited state, and make this like this. So this will become simply n0 comma dot 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 comma nl minus 1 number of particles in the L8 state, excited state, comma dot dot dot, the others remaining the same as it is. So what we'll get, if we do AL and AJ now on the same thing, n0, n1, and dot dot dot, then we'll get what, n0, n1, dot dot, and then AJ minus, sorry, nj minus 1, right? nj minus 1 number of particles in the jth state, comma dot dot dot, nl minus 1 number of particles in the lth state, and so on. Right now, okay, I am missing something here. Yes, there is the prefactor root over nl, right? And there is also two prefactors, root over nl and root over nj, right? Okay, now similarly, if you do the calculations, okay, al and aj dagger, okay, acting on this thing, and then you do, if you do aj dagger and al, similarly like if we have done for this case, right? For this case, if we do this thing for this case, and then if you just subtract these two things, you will get a l aj dagger, and what will get, just Kronecker delta jf. If you do that, you will get this thing. And similarly, you will get two more commutation relations for the bosonic state, AJ/AL, its commutation will be equals to 0, and which is also equals to 0 for AJ dagger and AL dagger. You can easily verify these two things using the concept that I have discussed in this video. So these are the basic things, okay, but this will not happen for the fermionic case, because for fermionic case Pauli exclusion principle comes into play, and for that reason there is only two cases can happen for any state, that state can be filled with one particle or that state can be empty, and for this only reason that commutation relations look different in the case of fermions, that we'll be discussing in the upcoming videos. So hope this video is helpful. Share this video to your friends and take care of yourself. Thanks for watching.